Hi, in today's video we're going to talk about the electronic configuration of anions. And so in today's video we're going to learn how to predict the charge of an anion based on that atom's electronic configuration. We're going to see that the charge an anion adopts is strictly related to the number of valence electrons it possesses and its desire to achieve a filled electron configuration. And we'll do lots of examples. So recall, based on our discussion of periodic properties, that the size of an element is greatest when it's down here towards the bottom of the periodic table. Okay, the size increases as we move down a group. The size is also greatest on the left-hand side of the periodic table. And basically what that does is gives unique properties to some of these elements in the upper right-hand portion of the periodic table. What kind of properties are those? They're small. They have high electron affinity, okay, so that means they like to attract electron density to themselves. And they also have a high ionization energy. It's very difficult to remove electrons from them, or more difficult. And so basically these elements in the top right hand corner of the periodic table, when you combine all these three properties together, the fact that they're small, that they like electron density, and it's hard to remove electron density from them, okay, so high ionization energies. What that tells you is that these elements are going to readily form anions. The way that they form anions is related to the electronic configuration of the nearest noble gas neighbor. And you might wonder why the noble gases are very unreactive, as we've said. Well, if we look at the electron configuration of neon here, we see that an electron configuration of helium and 2s2, 2p6. This gives us a total of 8 valence electrons, okay, and we'll talk about that later. But we'll also, if we look at the electron box diagram, we'll see that there's 2 electrons in the s orbital, spin up and spin down, and then we fill the p here, and we'll see that neon has a full complement of s electrons and a full complement of p electrons. We can represent this also if we were to put our dots around neon, representing the valence electrons as dots, and this works fine too. Any way you slice it, neon is unreactive because it already has a full complement of electrons. If we look at fluorine, okay, fluorine being 1 electron shy of having that full set. So it has an electron configuration, helium 2s2, 2p5. So when we fill in the electron box diagram for fluorine, of course, we know we're going to be 1 electron short. This vacancy right here, where we have room for 1 more electron, is what makes fluorine, okay, readily accept another electron and form the ion fluoride. And fluoride then has a 1- charge because this extra electron that would be readily accepted into that orbital is a surplus electron. In other words, it wasn't there previously. So now fluorine will find itself with 9 protons and 10 electrons. Right, 10 electrons if we count the 2 that are here in the helium configuration, and the 8 in the filled n equals 2 energy shell. Alright. So again, the vacancy in the p orbital means that fluorine is going to readily accept 1 extra electron, but would not accept 2 electrons or 3, but exactly 1. Okay, oxygen finds itself 2 electrons short of having that magical filled configuration. 2s2, 2p4. When we put the electrons in the orbitals here, 1, 2, 1, 2, 3, 4, we'll find that oxygen, as I said, can accept 1 electron here and another electron here. So that means that oxygen then finds itself readily accepting 2 electrons to form the oxide anion, and would form this ion by accepting exactly 2 electrons, not 1, not 3, not 4, but exactly 2. Alright, so let me ask you a few questions, and at this point it might be wise for you to pause the video occasionally to answer before I give the answer, and see if you're following along. Okay, so here we're wondering what charge will phosphorus likely adopt when forming an anion. So we got to locate phosphorus on the periodic table. Here I've just shown the p block. So here's phosphorus. Its electron configuration, of course, would be neon, 3s2, and then we count along the p block. This would be p1, p2, p3, so 3p3, and we find that that s orbital, of course, is filled, while the p orbital is going to have 3 spin up electrons but no spin down electrons, so it has 3 vacancies, 1, 2, and 3. So we would expect the phosphide anion to form as p3 minus, and for phosphorus to accept 3 electrons. Okay, same question. Now we're talking about iodine. Well, notice we already talked about fluorine earlier in the video, accepting 1 electron. And we're going to predict, based on the fact that fluorine and iodine are in the same group and they're both nonmetals, that we're going to also accept 1 electron. Now iodine has much more metallic character than fluorine, but still it's going to accept 1 electron and seek to fill that p orbital, same as fluorine, chlorine, bromine. Okay. Bottom line is all of your nonmetals in this group we're going to expect to form a -1. The -2 that we talked about for oxygen would also apply to sulfur, okay, being -2. Nitrogen, of course, -3. Phosphorus as well. Okay, but notice as you get towards the bottom of the periodic table, especially here, these cases with bismuth, tin, and lead, these guys, your metallic character increases as you move to the left of the periodic table and as you move down. So we're not going to anticipate the same behavior from all members of these groups, just especially the ones at the top right. Okay, what about selenium? Okay, selenium being here, okay, selenide. Again, we would expect it to adopt a +1 electron, +2 electrons, giving it a -2 charge. Okay, so in conclusion, remember that we said that we can predict the charge of an anion based on its location on the periodic table and its desire to fill that p orbital and adopt a -1, -2, -3 charge based on its location on the periodic table. Alright, thanks for watching and have a good day.